Hi, is this going to work? I guess it is. Very good. Good morning. My name is Pete Soderman. I'll be your speaker this morning. I'd like to welcome you all to Open Circle. For those of you that are new here today or this week, welcome. You have not as yet enjoyed our typical weather. Believe me, the last 2 or 3 weeks has been rather atypical. And it's nice to see that at least we can have this outside today. This is my first time speaking at Open Circle. If I'm a little nervous, I hope you'll give me a little bit of slack. I don't have anything to sell you this morning, nothing for you to sign up for. I don't have any books to autograph, although I'm writing one. I just sit back, relax, enjoy it. And hopefully we'll have a little fun. What I'm going to talk about this morning is neuroplasticity, which is a big word, a rather simple concept actually, and brain structure, the learning process. Primarily that's what I'm going to focus on, and how we can change our behaviors as a result of what we know about neuroplasticity and how the brain works. And we're going to finish up talking about neurogenesis, which is the creation of new neurons. We all grow new neurons all the time, regardless of what we do. We can't help it. It's something the body just does. What we do have control over, however, is how many we can grow and what we can do with them once they're there, because neurons are simply, as I'll explain, a use it or lose it proposition. If you don't use them, they wither and die. Why am I up here this morning? I'm not a neuroscientist. I'm not a neurologist. I'm a computer engineer by trade. Been in the business a long, long time. I'm just an ordinary guy who was willing to do a great deal of research into an area in which I have a vested interest. I am an ex-addict, a recovered addict, whatever term you care to use. I had a using career that began when I was 18 and ended in 1990. About 6-7 years ago, I became curious about addiction. I was working with somatics and started wondering why they behaved as they did. Why does this disorder make us act as we do? Why is it so hard for some people to get over it? So I did some research, not into the popular books and whatever. I started looking into scientific research. I mean, it's available to just about anyone. All you have to do is learn the language a little bit, and you can pretty much follow along. When I started into this research, I discovered a couple of things that kind of blew me away, because I wasn't expecting to learn either one. First thing I found out was that an overwhelming percentage of addicts recover on their own or with a minimum of outside help. They don't show up in treatment centers or hospitals or recovery groups or anywhere else. They simply recover on their own or with a little bit of help. And these are addicts who meet, or in some cases exceeded, the guideline or the criteria of the American Psychiatric Association for substance abuse and substance dependence. The second thing I found that blew me away was that according to the research community and according to the research that has been done, addiction is a biopsychosocial disorder. It's not a spiritual malady that addicts are powerless over at all. If it was, the huge percentage that recover on their own, and it's about 3 out of 4, by the way, wouldn't be able to do that. At that point, I kind of focused my research into, well, these people who recover on their own, how do they do that? Have there been studies? Has there been research into how they do it? And indeed, there has been. What are the things that work? What are the things that don't work so well? How do most people recover? And are there some techniques that will help them to recover? And it turns out that a large part of what we call addiction is learned behavior. Okay, we learn to become addicts. Yes, there are physical and chemical changes that take place in the brain, and many of those we can do nothing about. They're irreversible. However, what we can do something about is the part of addiction that's learned. And that's the direction my research took, and that's what I'm going to talk about primarily this morning. I'm not going to talk about addiction hardly at all. That's another talk for perhaps another time when my book's ready. I'm writing a book called Powerless No Longer, which looks at addiction from the standpoint of neurophysiology and neuroplasticity. If you talk to a neuroscientist 20, 25 years ago, what he would tell you is that beyond a certain point of during adolescence, the brain is pretty much fixed and immutable. New neurons weren't added, the brain couldn't change its structure. What you had was pretty much what you had. If you went out and killed brain cells somehow, they were dead, gone, those functions were gone, and so on. In 1990, an interesting research tool called the fMRI, Functional Magnetic Resonance Imaging System, was discovered. It's primarily a research tool, and it's like an MRI in that it images inside the body, but what it images, instead of organs and looking for different things that are wrong, it images blood flow. It shows neuroscientists what areas of the brain are active due to certain stimuli. What's growing, what's not growing, what areas are turned on by what, and so on. And what they found was, as was already read, experience can change the brain's physical structure and functional organization from top to bottom. That's called neuroplasticity. So neuroplasticity is a big word, which essentially means you can change your mind. And that's basically what it means. It's responsible for not only for our learning and unlearning, it's also responsible for the ability of some people to recover from serious injuries, strokes, and diseases that disable or disrupt some of their brain functions. We all know of people or have heard of people who have lost one of their senses, their eyesight, for instance, and a few months later find that they've developed more acuity in their sense of touch and their sense of hearing, etc. This is nothing but one area of the brain taking over an area of the brain that isn't used anymore or is used very little. We also are aware of people who've lost, they had a stroke on the right side of your head, which controls the left side of your body, so you lose movement, you lose your sense of touch. Through therapy and in many cases a lot of hard work, people can overcome this. And what's happening is, and we know this from imaging, is that other areas of the brain are taking over these functions from the area of the brain that was lost. We're all born with roughly 100 billion nerve cells called neurons. Most of these are located in our heads. There are a huge number, however, scattered throughout the body, and they're there for a couple of purposes. They are the brain's sensory network. The neurons in our body send impulses to the brain for pain, for touch, for other things, and they're also carrying information the other way for muscle control. And our muscles are controlled by our brains through neurons. Neurons have three parts. The center of the neuron is called the soma, S-O-M-A. It contains the nucleus of the cell and also all the little organelles that make a cell go. The input to the neuron is called the dendrite. Think of that tree, very broad at the base, tapers very rapidly. Dendrites are typically very short as inputs to the neuron, maybe a millimeter or so in length. The output side of the neuron, however, is called the axon, A-X-O-N. It's like an oil pipeline, okay? It can be as short as a millimeter or as long as a meter or even longer. These, again, if they're in the body, they carry inputs and outputs in both directions, to and from the brain, to control muscles and register pain. Each neuron connects to between a few thousand and as many as 100,000 other neurons. The point of connection, the point where the dendrite connects to the axon, for instance, is called a synapse. And I know you've all heard that word. A synapse is nothing but a gap, a millionth of a centimeter wide. Through those tiny gaps flow all of our thoughts, emotions, and sensory perceptions. The agents, I'll call them agents right now, that actually carry the information from one side of the synapse to the other are called neurotransmitters. And there's a whole bunch of them, and most of them are irrelevant for our discussion today. Two of them are dopamine and serotonin. There's GABA. There's a bunch of them. Not important what they are. They're generated by the neuron, and they actually carry impulse. They carry information from one side of the synapse to the other. The neurons are fired by a difference in electrical potential. Information coming into the dendrite causes this. If it causes that neuron to fire, it allows transmission across the synaptic gap on the output side, and that's how information moves through the brain. In the adult brain, the total number of these connections, or synapses, are somewhere, for most of us, between, let's say, 500 trillion and 1,000 trillion. 1,000 trillion synaptic connections are possible. Synapses that are not used are pruned away. As I think I mentioned, neurons and synapses are a use it or lose it proposition. If you don't use a particular connection, it withers and dies. The brain is very efficient that way. There's only so much blood, there's only so much nourishment, so it's only going to nourish and support the circuits that we're using.